So this was the expression I is equal to CVF. We have discussed it. Now there is a numerical related to this this expression. It is given that we have a potential difference of 180 volt, a frequency of 50 hertz, and the average current in the ammeter is 2.5 microamperes. Now we need to find the capacitance, right? So we know the expression. We have I is equal to CV into F. We know the value of current, we know the value of voltage, we know the value of frequency. We can just plug in the values and we can get the answer. We just need to know the prefixes. Basically 2.5 microamperes means 2.5 into 10 raised power minus 6 amperes, right? And the capacitance is we need to find the capacitance, and the voltage is 180 C into 180 into 50. You can just divide the value of to find the value of C. We can just divide the expression on the left with 180 and 50. If you have calculator, you can just give it a quick check. There, what is your answer?
2.7. I mean 2.7 times 10 to the power negative 10.
2.7 into
2.78 times 10 to the power negative 10.
all right, 2.78 into 10 raised power minus 10, right?
Yeah.
Minus 10 farad. But it is asked that we need to find the answer in picofarads, and we know pico is 10 raised power minus 12. So we need to move this decimal from
Divided
left
by,
to right. Yes.
Multiplied by 10 to the power.
Yes, multiply by 10 raised per 2 and then again divide it by 10 raised per 2. So we will get 278 into 10 raised per minus 12 farads, or you can write it 278 farads, or you can just you can change it from 2.78 to 2.8 to simplify it, to simplify this expression. And so your answer will be around 280 picofarads. You got it, Rani?
Yes, sir.
Okay, so let us move forward if you are clear with this concept. Okay, the next question is we have a second capacitor and it is connected in the circuit of figure 6.2. The two capacitors are now connected in parallel. State and explain the change, if any, in the average current in the ammeter. Now it is asked that we need to find that what will be the change in the in the current of the ammeter if we connect another capacitor in parallel in this circuit. So you need to remember the formula of equivalent capacitor both in case of series and parallel combination. In case of series combination, we know that in case of capacitance,
1 by C.
yes,
1
by C equivalent will be equal to 1 by C1 plus 1 by C2. So C equivalent will be less than, in this case, C equivalent will be less than both C1 and C2, right? But in case of parallel combination, we know that it is C equivalent is given by we know that C equivalent is given by C1 plus C2, exactly. So it means that in this case C equivalent will be more as compared to C1, right? The initial capacitance we had. So it means that if we have more capacitance in this case, so it means if we connect more capacitance in this circuit,
current will be more.
yes. Why? Because there will be more charges stored on the capacitor. So it means that more charges can flow through this ammeter. So it means that more current will be flowing through this, right?
Yes.
Okay. So let us move forward to the next question. If you have any question about this, you can ask Rani. Or is it clear?
It's clear.
Okay. So the next question is also of the similar sort. We have a double switch. we can connect it with X as well as Y. When we connect it with X, we get the capacitor to be charged, and when we connect it with the Y, the capacitor discharges through the ammeter, right? Now the data given in this question is that the ammeter records a current of 4.5 microampere, and we need to find the charges that will be flowing through this ammeter. So by definition of current, we know that I is equal to Q by T, right? We need to find the number of charges flowing through this ammeter in 1 second. So we just multiply, in order to find Q, we will just multiply current time into time. Time is 1 second and current was 4.5 microamperes. So it means that the charge that the charge flowing through this ammeter will be Q is equal to 4.5 into 10 raised per minus 6 uh, its charge, so
Yeah.
it will be coulombs, right?
Oh yeah, cool. Yes.
You got it?
Yes.
Okay. So what is the next part of this question? The charge on one plate of the capacitor, each time that it is charged, we need to find the charge on one plate in this case, right? So it means just give me a minute to have a look at it. Uh, Rani, in your marking scheme, its answer is 9.0 into 10 raised to power minus 8 coulombs. But in my opinion, it shouldn't be like that. Basically, just give it a try. Just divide 4.5 into 10 raised to power minus 6 with 120.
Divided by 120.
Yes.
You will get 3.75 times 10 to the power negative 8.
3 point?
75 times 10 to the power negative 8.
Okay. The answer here is 9.0 into 10 raised to power minus 8. Okay, I will check it after the class. I don't know why the answer is not right in this case, but I will just send you a voice note and then explain it in that voice note. Okay, Raini?
Yes, sir.
Okay, so the next part is about the capacitance, and now we know that the capacitance is equal to, we know that Q is equal to CV, right? We are given with the potential difference. We have find out the charge in this expression, so we will just divide this value of charge with the potential difference, which is 120, and we will find out the value of this capacitance in farads, right, Raini? Is it clear?
Yes.
Okay, so in the next expression, in the next question, it is asked that a second capacitor having a capacitor equal to that of C is now placed in series with C. Suggest and explain the effect of current recorded on the ammeter. We have discussed
Here the
the
current
similar
will be
question.
greater.
No, the current will be decreased because now the
Oh yeah, because it's
capacitors are in.
1 bar. Since
Yes,
series it is 1 bar, so it will be
exactly.
okay.
Because they are in, you can say, in series combination now, and in series we know that they will be will be the reciprocal of the capacitance. So that's why the capacitance will be decreased, and if the capacitance is decreased, so the current will also be decreased, right, Tiny? I hope you are clear with this question. I will explain this part later on, right? I will have a quick check on it. Fine, Raini?
Yes, sir.
Okay. So let us move to the next question. Okay. Should we do this question first, or now we should move towards the first
We
question?
can start from the first question itself.
Okay. So this question, basically these questions are about the ideal gas, right?
Well,
This
yeah.
this question is very simple and easy. You will see how. Basically, in this question, let us have a read of this statement. There is a cylinder of constant volume. We are given with the volume, right? Which is 4.7 into 10 raised power 4 centimeter cube. And it contains an ideal gas at a pressure of 2.6 into 10 raised power 5 pascal, and the temperature is 173 degree. The gas is heated. It means that we give some energy to the gas. Whenever we heat the gas, it means that we are giving some energy to the gas, right? So how much energy we are giving to the gas? 2900 joules of thermal energy we are providing it to the gas. Now we want to find the final temperature, pressure, and gas are this as an expression. So first of all, we need to find the value of number of molecules. Now, before solving these type of numericals, you need to convert all the data in system international units, right? You can see that here volume is given in centimeter cube, but we need to find the volume in meter cube. Similarly, the
Meter
temperature
cube.
is in degree centigrade, but we need to have the temperature in Kelvin scale, right? So how can we convert this volume? We will just
Um,
4.7 into
you have to
10.
divide it by 1 times 10 to the power 6. So you will get 0.047.
uh, it will be just 1 into 10 raised power 2 cube, right? We just
Yeah,
multiply
6.
it by we will just divide it by 100 cube, because we are converting from centimeter cubes to meter cube, right? So in this way you can convert the volume. And similarly, in case of temperature, in from degree centigrade to Kelvin centigrade,
273, right?
273 plus 173, right? Right, Rani?
Yes.
So now we have converted the data. We know two expressions of ideal gas, right? Which is PV is equal to nRT, and there is another expression, PV is equal to
KT.
nKT. Are you familiar with these expressions?
Yes, but what's the difference between the first N and the second N, like the small N and the capital N?
Yes. So basically, the small n is number of moles. The small n is number of moles of the gas, right? And this capital N is basically the number of molecules. The capital N is number of molecules,
Molecules.
right? Now they have a relation among them as well. Basically, the small n is number of molecules over Avogadro's number, right? This is the relationship between them, right? The number of moles are basically number of molecules divided by Avogadro's number, right? So this is the relation between small n and capital N. Similarly, we have a relation between R and K as well, right? So just if we put plug in the values of small n over here, so we can find that K will be equal to R divided by Avogadro's number. This is the relationship between K and R, right? That if you, let us say, if you forget the value of K, you can find it. Are you familiar with this Avogadro's number, right?
Yes.
Okay, so that's fine then. If you, let us suppose you, if you forget the value of K and you remember the value of R, so you can just divide it with Avogadro's number to find the value of K. Or if you just forget the value of R and you want to find the value of R, you just multiply Avogadro's number with K and you will get the value of R in this
The
case,
value, oh, okay, R. Yeah. But these
right?
are given in the formula sheet, right?
Yes,
All
these
the
values
values.
are
Okay.
generally given in formula sheets, and you do have these value of these constants in your calculator as well, right? In your
Yes.
calculators, you do have these values as well. So now moving towards coming back towards the question, we can use both of these equations. Why? Because for the initial conditions we have complete data. We do have the value of volume, we do have the value of pressure, we do have the value of temperature, and K and R are constant. So we can use both of these formulas to find the value of number of molecules. But this is the second formula, which is PV is equal to NKT. This is a more direct method, because in this we can directly find out the number of molecules. In this case, if we use PV is equal to small nRT, then we will get the number of moles, and then we again use this formula of number of moles to find the value of n. Then again we will multiply this number of moles with Avogadro's number to find the number of molecules, right? So we can use both of these formulas, but this second formula is a more direct method. Are
Right.
you
Okay.
clear with this, Raini?
Yes, sir.
If you have any question
Yes,
about
sir.
this, you may ask.
No, sir, it's fine.
Okay, so let us move forward. Okay, in the next question, we need to find the increase in average kinetic energy of the molecule during the heating process. We need to find the average kinetic energy, right? The increase average, if we have these total number of molecules, right? And we are given that we have added this much heat. It means that for all these molecules, the total kinetic energy is increased by this amount, 2900 joule, right? And for one molecule, how can you find the average? Let us say we have three numbers, 5, 7 and 9, and if you want to find the average of them, then what will you do? You will add all of
Add
them,
all of them and divide
then
it by
divide it
3.
by 3. Now we have total number of molecules, let us say 3, and total energy given to this system is 5 plus 7 plus 9, let us say that is 2900 joules, right? So you need to divide this 2900 joules by the total number of molecules in order to find the average increase in kinetic energy. Do you get my point,
Um,
Raini? Oh, okay, let me explain it again. Basically, let us say we have total number of molecules which are equal to n, right? We have total energy which is 2900 joules, right? It means that the total energy which is increased for n molecules is 2900 joules. Is it clear till this point?
yes.
Now
Yes.
we, in this question we are asked that we need to find the average kinetic energy, right? So total kinetic energy, it means the sum of all the values is 2900, and total number of values is n, and we need to find the average. So we will just divide the sum with the total numbers to find the average.
Okay. Okay, sir. I
Is it
got it.
clear?
Yes.
Okay, that's fine then. You just need to divide this 2900, because it is given in the question that we are providing 2900 joules of heat, right? So it means that we are giving this 2900 joules to the kinetic energy store of all these molecules, right? And if 2900 joules of energy is given to the kinetic energy stores of all the molecules, and we need to find the average, so we just need to divide this 2900 joules with the number of molecules, and number of molecules we have find out in this expression in this part 1. So we will use this answer in the second part to find the average kinetic energy. You got it, Rani?
Yes, sir.
Okay, so let us move towards the next part. In the second part, use your answer in part 2 to determine the final temperature in Kelvin of the gas in the cylinder. Now we need to find the total, the final temperature, right? We know the expression of kinetic energy del Ek is generally equal to 3 by
3
2
by 2 RT.
K K del T.
Wait, I don't know that formula.
What was your formula which you were telling me?
3/2 RT, right?
3/2
RT.
RT. Okay, just give me a second to tell you that how we will get this. I told you the relationship between K and R, right? The relationship between K and R was, if I write K, it is equal to R divided by Avogadro's number, right? And it means that, okay, this is the total energy, the total energy for n molecules, right? This is the total energy for n molecules, 3/2 RT. Now, if you want to find the total energy for one molecule, what will you do? You will write 3/2 RT divided by n. Is it right till this point?
Yes.
Now, R is equal to, we know that R is equal to K times NA, right?
Yes.
So what will we have? We will have, let us plug this value in this expression of R. 3/2 K and NA T over N. And we know that small n is equal to n divided by NA, right? So NA divided by N will be equal to 1 by small n. So it means that this is the energy for for 1 mole of the gas, right? So that's why we have write this formula 3/2 K del T. We often use this formula for the kinetic energy store of the gas molecules, right? So you can directly remember this. All this story I have told you is just for your concepts. You can directly use this formula 3/2 KT, right, Raini?
Yes, sir.
Is it clear? If you have any doubt, you may
Yes.
ask.
Won't it be 3/2 KT by N?
Because we are just telling you that this is for 1 mole of the gas. This energy we have find out the kinetic energy for 1 mole of the gas in part 2, right? So that's why we have directly written it. We will just plug in the value for the 1 mole. So if we divide it by Na, again, what will this mean? This means that it will be for 1 mole of the gas, right? Or small n. So what does this mean? It means that the kinetic energy for 1 molecule of the gas, and if we just directly plug in the value of del ek for 1 molecule, so that's why we can directly write 3/2 K del T, right, Raini?
Yes.
Because we are going to plug in the direct values of del ek, which is for 1 molecule or for 1 mole. You got it?
Yes, sir.
Okay, so let us move forward. We know the formula, that is 3/2. Moving back to the question, which is 3/2 K del T. Okay. Okay. Ek is equal to 3/2 K del T. We have find out the value of kinetic energy for one molecule in this part, and its value will be something like 1.5 into 10 raised power minus 21, right? And it will be 3/2 into the value of K is 1.38 into 10 raised power minus 23 into delta T, right? Now you will just rearrange all these values and you will find that delta T will be equal to 70 Kelvin, right? But now here is a trick. It is asked that we need to find the final temperature, not the difference in temperature. So for that, what will we do? We know that delta T means final temperature minus initial temperature, and it is equal to 70 Kelvin, right? So initial temperature is now important. we are given in the question, you can see here that the
Final
initial
temperature.
temperature, the
No.
initial temperature
Go
was
ahead, continue.
173 degrees centigrade. So 173 plus 273 is about 246 kelvins, right? So what will we do for final temperature? TF will be equal to 70 Kelvin plus initial temperature, and which is 446, right? So the answer of the final question will be final this temperature will be something, you can write, it will be 516, I guess. Yes, it's something 516 Kelvin, right? So this is how you will solve this question. Is it clear, Rani? If you have any doubt, please ask the question.
No doubt, sir. It's fine.
That's great. If it's fine, then let's move forward. Okay. In this question, it is asked that there was a student who set up an apparatus in order to find the melting of ice, right? In this apparatus, you should have a look at the components of this apparatus. We have a voltmeter, we have an ammeter, we have a battery, we have a heater, we have pure ice, we have beaker, and we have water. And where this water is coming from? This water is coming from this melting of ice, right? And basically through this apparatus, we are observing this melting of ice, right? So let us see what is asked in the question. So before the question, some data is given. Basically the values of voltmeter reading and ammeter readings are given. Similarly, the initial mass of beaker plus water, initial mass, and the final mass of beaker plus water is given, and the total time for this collection of mass is also given, right? So there is another thing which is specific heat of fusion. Do you have the concept of specific heat of fusion? What does this mean?
Yes.
What does this mean?
Specific latent, it's the energy required to turn unit mass of
Yes.
solid to liquid at constant temperature.
Exactly. This is what specific heat of fusion means. So we are given with this. Okay. So in the first question, what is asked? It is asked that state what is observed by the student that shows that the ice is melting at a constant rate. That how can you tell from this experiment that the ice is melting at a constant rate? It was given in the question, I guess, that yes, it is given that pure ice is melting at the constant rate. But the question in this question, he is asking that how can you tell that this ice is melting at a constant rate? So we can tell this if the you can say if the volume of this water is increasing at a constant rate, right? If this volume of the water is increasing at the constant rate, then we can say that the ice is melting at the constant rate, right? Or if there is another thing from which you can tell that the ice is melting at the constant rate, which is if these drops are coming out from this nozzle at a constant rate, so then again it means that the ice is melting at the constant rate. This was the question, that you need to tell that how we can conclude that the ice is melting at a constant rate. So from observing this water, the volume of the water, if it is raised at a constant rate, then we can say why, because this water is coming from the melting of ice, right? So if the water is
Yes.
increasing at a constant rate, so it means that ice is melting at a constant rate. So by observing this, we can state that the ice is melting at a constant rate. Is it clear,
Okay.
Raini?
Yes, sir.
Okay. So the next question is use the data in figure 3.2 to determine the rate at which thermal energy is transferred to the melting ice. Okay. We need to understand one thing first before solving this question. We need what we need to tell. We need to tell the rate at which thermal energy is transferred. Now, just understand that what is energy transferred per unit time. It is basically power, right? Do you have this
Yes.
concept that power is work done per unit time or energy transfer per unit time? So it is asking that we need to tell the rate at which the thermal energy is transferred. So it means it is indirectly asking for the power. So we need to find out for the power, right? So it means that if we can find out the total energy and then divide it by the time, we can find out that how much thermal energy is being transferred to it, right? So how can we solve this question? Basically, in this question, we are given with the initial and final values of masses. We know that what is the formula for the latent heat of fusion. We know that it is delta Q is equal to delta ml. Are you familiar with this formula where L is the latent heat of fusion of that material? Are you familiar with this formula,
Yes.
Raini?
But isn't it E equals ML?
Sorry.
Isn't it E equals ML?
This is just a representation. Basically,
Oh,
delta Q
okay.
is also a heat or energy, and E is also energy, right? So it is both of them are right. Let us say if you are convenient with E, let us put it E, right? You can
I
write.
thought Q is charge for some reason.
No, no,
So I
no,
was
no.
like,
In this case, it is just energy, right? Q is heat. I was representing heat by Q. But if you are comfortable with E, we just write it EL, right? For energy of fusion. Okay. So this is how we can find. Now we are given with the final mass, and we are given with the initial. We are given with the final mass value of mass and the initial value of mass. So it means it means that we can just plug in the
63.5.
values. We can just plug in the values. Yes,
63.5.
yes,
That 63.5 is the change in mass.
yes. And we will just multiply it with this value of L, which is 332 joules, right? And we will find out that how much energy is transferred by this. Are you clear with this, Raini?
Yes.
Are you sure?
Yes.
If you have any
So where did you get the value of 332 from?
sorry,
Where did you get 332 from? You said L
it's
was
it's given.
330.
It's the value of L is
Oh
given
yeah,
here.
it's given specific latent heat.
Yes,
Okay.
it is given in this question, right? So this is how we can find delta E in this case. You got it, Raini?
Yes, sir.
And
Yes, sir.
the other question is that we need to find the thermal energy is gained from the surrounding. That how much thermal energy is gained from the surrounding. So can you tell me that how we can solve this part, this particular
Thermal
part?
energy gained from the surrounding.
Yes, just give it a look and then
Is
we
it
will.
MC delta T?
Sorry.
No, MC delta T, or is that for
Uh,
specific?
okay,
No.
let me tell you. Basically, if we solve this question, right, the total, we will find out the energy. Okay, let me explain it to you in the steps. Do you have a calculator so that we
Yes,
can
sir.
we can have a proper look of this question? Okay, just subtract 185 from 185 121. Just subtract that and multiply it with 332.
You will get 21082.
Okay, we will get 21082 joules, right? And it is
Yes.
given that we are giving this heat for 5 minutes. And remember that we need to find power. So we have to divide it with time, right? So it means that for this power 21082, we need to divide it as it is in minutes, 5 minutes. We need to divide it 5 into 60,
60.
right? So what will be the answer for this?
70.27.
70.27.
27.
27, right? Watt. Okay, exactly. Now, in the second part, try to understand, Raini. It is asked that how much heat is being gained by the surrounding. So, how can we find it out? We have find out that total heat is given to the rate at which total thermal energy is being transferred is 70.21. We are given with the value of voltage and current over here. So again, we can use this data to find a power from this formula as well. So it is P is equal to VI. So just plug in the values. 12.8 multiplied by 4.60. What will you get?
4.8 into 4.60.
Yes, what will be the answer?
It'll be 58.88.
58.88 watt, right? Now try to understand it in the second part. Let me show you the question. In the second part, it is asked that you need to tell that how much thermal energy is gained from the surroundings. We have find out that total thermal energy gained to the sound by the system is this, and this much energy is transferred by the heater, which is using this current and voltage. So if we subtract from 70.21, if we subtract 58.88, it means that the remaining power will be delivered by the surroundings, right? This the answer of the 70.21, it will be something 11.6 or something like that, right? So it
70.21 minus 58.88. Yes.
yes, it will be something
You
11
said
points.
11.33.
All right, 11.33. So it means that this much of power is delivered by the surroundings, and this much power is delivered by the heater, which is using this current and potential difference. And so the total power thermal energy is being transferred to the system is this much, right? If we sum these two, we will get this answer. So this is how we can find it out. Are you clear with this concept, Raini?
Okay, so this P equals VR, we are using it to find the power dissipated by the heater, right?
Yes, P is equal to VI. We are using it for the power being dissipated by the heater, because in
Heater?
this question you can see from the figure that it is connected to a voltmeter and ammeter. So from the values of these readings, we can find out the power of the heater. So this is the thermal energy being transferred to the system by the heater, and we know that total energy being transferred to the system is this. So we will subtract this value from the total value to find that how much power is being transferred, or you can say energy is being transferred to the system by the surroundings. Is it
Okay,
clear?
and yes, and P equals delta E by T, that is for the uh, thermal energy of the system, right?
Yes, exactly.
So then you're subtracting both of them to find out the
Energy which is being obtained from the surroundings, right?
okay,
Because there is
okay,
no other
sure.
way. Do you get it?
Yes.
Okay, that's great. Okay, Rani, let us move forward if you are clear with all these things. Okay, the next question is again about the ideal gas that undergoes. For this question, you need to remember a few things. First of all, you need to remember that work done is given by V is equal to P del V, which means that if the volume of the system is constant, so it means there will be no work done. First thing is this. The other thing is that the internal energy is a state function. Internal energy is a state function. I am just giving you the overview of this question, right? Internal energy is a state function. What does this mean? It means that in a closed cycle, total internal energy will be, the change in total internal energy will be zero, right? And the last point is that you need to know the first law of thermodynamics, right? So what does this? Delta Q is equal to the change in total internal energy plus the work done, right? Are you familiar with
Yes.
this?
Yes.
So if
What
you
was the point? Internal energy is.
a state function. State function means that it is such a function that if we take it in a closed cycle, then let us say we started from the P and moved towards the R, and from R to Q, and then again from Q to P, then it means that we have moved from in a closed circle, that we finished where from where we started, right? So in such cases it means that the total energy will be same in all those functions which are state functions, or such functions which are in which the change in a closed cycle will be zero, right? Have you got it, Raini?
Yes. The state function is where the total energy change will be zero.
Yes, in a closed cycle you need to remember that,
Yes.
in a if we move in a closed cycle, then that will be zero, right, Raini?
Yes.
Okay, Raini, the meeting time is getting over, so I will just share the link again, and please connect it again, so that we can just have a quick look at this question, right?
So,
Okay, I am sending you the link right now. Okay.